Okay, maybe we can start. Good afternoon, everybody. So Joydeep will continue his second lecture on effective field theory. Okay.
Okay, can you please check the recording is going on? It's going on, right? Yeah.
Yes.
Okay. Okay. So thank you, Sanjay, again for organizing this lecture series. So yesterday, as you can recall, so we have actually broadly discussed that what are the features of effective field theory, and though it's being a very old subject, why and there is rebirth of this effective field theory approach in last 6-8 years. And actually there's a new development in the techniques of this effective field theory, and specifically why this era in particle physics, when experiments in the experiments, there are lots of null results are coming up. It's basically saying that okay, there's some desert region after the electrosymmetry begins scale, and this actually somehow giving a boost to look for the effective field theory approach, because as we have discussed yesterday, that to validate the effective field theory, there must be some separation of scales such that the two scales are widely separated, and we can truncate and we can use some kind of effective field theory approach. And just to recall what I discussed yesterday about the main theme of those effective field theory, there are three broad pillars are there. One is the bottom-up approach, where we have there is no notion of UV theory. We do not have any clue. And when I'm saying there is no clue, of course, I am not saying that theoretically, rather I'm saying experimentally. From the experimental side, we do not have much clue what kind of new physics are there beyond the standard model. Okay, but that should not stop us for thinking about the how we can gather more information even without knowing that in great detail. So that's the beauty of this effective field theory in a bottom-up approach. And we'll see today that how that formalism works. So today's approach will be a bit more mathematical and in that way. And then tomorrow we'll be discussing the complementary approach that I talk about is the integrating out at the top down. You start with your favorite theory, and effective field theory gives you a good handle. Just okay, so you have a full theory, but it's not always necessary to focus and or distribute your focus all the way in the different parts of the UV theory. Rather, depending on what kind of data you want to use, relying on that, you can focus on specific kind of interactions in the UV theory, and then you construct an effective field theory out of that, and how that can help you to address and perform a comparative analysis. And then after that, we'll move to the more phenomenological approach, where with these effective operators and along with those different kind of experimental data, which is basically, for example, the Higgs data or the electroequation data, along with that, what are the best comment we can pass on, and also we can check that okay, though we propose different kind of theory or the prescriptions, for example, two-Higgs doublet model, or for example, let's say different kind of neutrino mass models, or you extend sometimes your theory by leptoquarks and so on. So it appears that they are slightly different from each other. But now, effective field theory, from the effective field theory perspective, we'll see that are they really different from each other? And if so, how much degeneracy they would have? And that will give us an idea, and specifically from mostly to our experimental colleagues, that is it really possible to discriminate these different theories based on the data we have, or what are the best scenario we could have? So let's start today's thing, which is the bottom-up approach. So we start with some low energy theory, where we have this infinite degrees of freedom. So when I'm saying infinite degrees of freedom, that means basically you are working in energy scale, and that energy scale is sufficiently large enough to produce the massive particles of those infinite degrees of freedom. For example, if you are working in the standard model, when I talk about the standard model as my infinite degrees of freedom, that means basically I'm working with, let's say, a few hundred GeV is my energy scale, such that I can produce all the standard model particles on shell, right? So that is my low energy theory. Now, having this low-energy theory, what are the informations we have? We have the information about the symmetry. And when I'm saying the symmetry, again, let's try to recall. It's not only about the gauge symmetry, it's also the global symmetry. It can be accidental, for example, baryon number or lepton number, or of course, you have the space-time symmetry, which we cannot be ignorant about that because space-time information is very important, right? And then along with this symmetry and this information about the particles or the quantum fields, we can construct the effective operators. This approach is basically very generic, the way we construct our Lagrangian. So if you recall, how do we construct the Lagrangian for the standard model? So you are given the symmetry and this thing and particles, you know how do they transform, right? And then you try to check by hand, different kind of invariants. Okay. Okay, so like psi bar psi phi, psi bar psi. Similarly, the Lorentz symmetry will not allow you something like psi bar psi psi. 3 fermion field. It's always multiple of bilinear in fermion thing. So all are taken care of, but the problem in the context of effective field is that number of operators that will be generated for higher and higher dimension are larger and larger. So the manual approach sometimes would be very misleading. So we want to avoid that and then try to prescribe something more mathematical and robust where it will be less erroneous. So this part also I mentioned that this mathematical principle is completely based on basically the Hilbert series approach, where we need to construct something called the plethysticks, and then we use those plethysticks and perform the integral in the group space, and from there we calculate the invariance. But why I'm displaying this thing to keep your focus mostly on this chi-r, which is the character. So that's you can see that these are the Spurion fields that you throw by hand, and this chi-r are the character of those representations, right? So first you have to learn how this chi-r you can compute. So this is the first thing that we need to learn. That okay, so we have this when we talk about the representations, those representations are basically my irreducible representations, right? And these z that we talked about yesterday are basically my maximal torus coordinates, which are basically either you can think of the epsilons or the z's. Now this m epsilon, which is written in this particular form, and these epsilons are such that the product of these epsilons are basically identity. Okay, and this diagonal way of written here is that it's actually the representations of any kind of irreducible representation you're talking about. For example, we'll do some example that will be more clear. So this is function of these epsilons, and now the character associated with these irreducible representations is written like this ratio. Now, what is in the numerator? This numerator is a compact form written, which is the determinant. Okay, so now you can read this thing that okay, there's some epsilon 1 to the power r1, epsilon 1 to the power r2, and so on, and it goes up to epsilon 1 to the power 0. Now you can see that for SUN I'm working on. So for SUN, how many independent so diagonal generators are there? Maximum number of diagonal, that's the rank, that's n minus 1. So this number of r is also n minus 1. Okay, and that's why the Rn is basically 0, and that's why it is 1, epsilon 1 is 0. Okay. And number of epsilon is also depend on basically what is the rank of the group and plus 1. That means I would expect that n minus 1 number of variables or coordinates should be there. But here I have n numbers, right? So that means not all of them are independent. They are related to each other. And that's why I said the product of the epsilons is basically 1. And that gives an additional constant. And that's why though you write down this determinant in terms of n variable, but effectively there are n minus 1 number of variables. And then we have this denominator. So denominator is also written in this particular determinant form, which is basically epsilon 1 to the power n minus 1. And this n stands for which SUN you are working on. Okay, and that you will write down in this particular form. Now, as I'm saying, there's a one-to-one correspondence with the representations and its character. That means if I giving you a group and I define some kind of representations, okay, its character function should be unique. Now, if you look at the then you'll find out that okay, the epsilons, which are the property of this group, are there. Okay, the n for SUN, this is fixed. So in the denominator, there is nothing which actually, are different for different representations. So this denominator function is basically independent of the representations. That's why the character function, this quantity, once you compute for a given group, that will be automatically appearing for all the representations. Now the question is, okay, fine, but now then, what is the source of this unique feature of the representations? That's the numerator. Now in the numerator, if you see, the epsilons are basically a property of those group again. Now the small r are the features which the value of them are different for different representations. So this small r actually captures the effect of different representations. So that's how, if we can compute this small r, yes. So now, if we can compute these epsilons, okay, for this given group, and then for different representations, if we can compute this small r, then we should be able to calculate the character functions. Okay, so that is the ultimate idea, how to calculate the character functions. Yeah, so up to this part, any question? Okay. So now, so this determinant part, which is that appearing here in the denominator, that is another, yes.
Sir, epsilon what are these epsilon? Epsilon R1, epsilon R2.
Epsilons, okay, so epsilons are basically my torus coordinates, and they satisfy, yeah, torus coordinates. Okay, so if you remember, in the last time we talked about the U1 case, the dz by z. So z's are also the torus coordinates. Here the epsilons are also my torus coordinates, but these epsilons, how they are related to z, because in vector space you can have a choice of basis is not unique, right? You can change the basis. So this is written in terms of epsilon basis coordinates, and we'll see how we can rewrite this epsilon in terms of z, because everything we have to write down in terms of z basis. Okay, and we'll see how to write down that thing. Okay, and these epsilons are related to each other by this constant, and each epsilons are basically unimodular. Okay.
Okay, thank you.
Okay. So now what I was saying, that the denominator is not only appearing in this character function, but also when calculate the group space measure, which is called the Haar measure, when you define that thing in this way, okay, so then this denominator is playing another role here. So this delta epsilon is nothing but this denominator function. So now you can see that Haar measure is the group space invariant, that should be independent of the representations. And as we have learned that there is no quantity here that differs for different representation. That's why this quantity delta epsilon, okay, is independent of the representations for a given group. This is a fixed quantity, okay, and that help us to define the Haar measure. So in the Haar measure, there is no dependency of the representations, and that is what expected. Right. So now let's try to recall that what is my Cartan matrix for this SUN group. So basically, if you think about how this Cartan matrix you can write down directly from the Dynkin diagram. So for SUN, you will just write down some n-1 number of block, and each block is basically connected by a single line. Okay, that is the Dynkin diagram. And so my Cartan matrix is basically 2 -1 -1 2, and it replicated, up to this n-1 times. Why? Because SUN has a rank n-1, so it will be a n-1 by n-1 matrix. Right. So now once you have this Cartan matrix, and then for any SUN group, you can write down the lowest dimensional fundamental representations. So here, some of the literatures write down the very bad definition of fundamental representations is that, the fundamental representation are those which is the lowest dimension. But that is not true, because for any given group, there could be multiple fundamental representations. And how many fundamental representations could be there? That depends on the rank. So if your group has rank n, then you will have n number of fundamental representations. So for SUN, we'll have n minus 1 number of fundamental representations. Okay, but we'll focus on the lowest dimensional fundamental representations. And the lowest dimensional fundamental representations are written as in this way. You have used the Dynkin index as 1 and all the other elements are basically 0. Okay, so then once we have this information, then we can calculate something called the weight tree. How to calculate the weight tree? What you do, you start with 1 0 0 0 and then you subtract each row from this. So basically, let me call these row are like alpha 1, alpha 2, alpha 3 up to this alpha n. And then I can calculate the weight tree by this quantity minus alpha 1. Let me call that L1. And the next one will be L1 minus alpha 2, which I call L2, then L2 minus alpha 3, and so on. And it will continue till you hit basically a level which is all 0, the last element is minus 1, and then automatically you will stop. So that's how you get basically the weight tree. And the number of elements that will be generating, that will match basically the dimensionality of the representations. That's one of the beautiful check you can do. So this is the, we'll discuss this thing again with an explicit example. I think that will be more easy to visualize then. So then our next task is basically to write down the the torus matrix. So this is the torus matrix for SUN. Here I am writing in terms of epsilon coordinates, so that's why it's a n by n. Okay, but you can see that this is written in terms of epsilon e to the power theta 1, e to the power theta 2 minus theta 1, so on. And here Zi, which are basically the U1 copies are n number U1 copies are there. So you can write down Z's are basically similarly the way we define this, Z as e to the power I theta for U1. Now you have a multiple U1 and each U1 have their own theta i's. So this is a Zi equal to e to the power theta I. So that's why the first element is basically epsilon 1 is your Z1, but epsilon 2, now you can see it's like a Z1 inverse, Z2, and so on. And the last element is basically Zn minus 1 inverse. Now you can see that though you have an n number of epsilon, but not all of them are independent, but the independent coordinates are n minus 1, and that's why we have n minus 1 number of Z. Okay, so that's why in this way we can translate our epsilon basis to Z basis. Fine. So this is not sufficient enough, because if you can recall in this computation, what we had actually, we need to learn how to calculate these R1s. So we have translated these epsilons to Z's, and that will give us uniformization in the defining the Haar measure, that now everything I can write down in terms of Z, because I know how these epsilons are related to Z. But the next level task is basically how to calculate the R. So to calculate the R, we need this vector relation. This R is basically lambda plus rho. Okay. So now you see rho is basically defined rho I as n minus I. So rho is a vector. For SUN, you can see that you start with n and then you go n minus 1, so on. So you can define your rho I vector. So to calculate the rho vector, you don't need to know anything, because you know each element starting from the SUN. Okay. So effectively, if I calculate the lambda, then I can calculate the rho. Sorry, R. So now how can I do that thing? So let's see an example with that thing. So let me introduce one representations. Okay, I don't know what is the dimensional representation, but what I know basically the Dynkin level is given in this particular form, A1, A2 up to this An minus 1. And now this elements of the weight tree, what I discussed, that you start with the lowest dimension fundamental represent highest weight, and then you subtract your alpha 1, alpha 2, those Cartan row of the Cartan matrix, and you get all these elements. And now you can see what I was telling, that you stop where you'll get this quantity all 0 and the last element is minus 1. So interestingly, they form a kind of a basis. And now you know from the vector space that if you have a basis, in that basis you can write down any vector. So that's what we are doing. So Dynkin level for any representations that I can write down in a basis of this weight tree, where the coefficients are basically my lambda 1, lambda 2, lambda n minus 1, and up to lambda n. So now, as an input, if you think what you are providing, this quantity, because you know for a given theory what are the representations, and if you know the representations, just you consult any literature, you will get the Dinkin levels. You have the information of the A1, A2, A3, all those things. You know the these weight trees for a given group, but you do not know lambda 1, lambda 2. What you can do, you can invert this relation. And if you invert the relation, then you write down all the lambdas in terms of A's. So now effectively, you rewrite these unknown quantities in terms of the known quantities. So in this way, you can calculate the lambdas. And once I know all the element of this lambda, that means that I can construct the lambda vector, rho vector, I know a priori from this quantity. So I'll just add them and I'll generate this R. And once I know R, then automatically the R1, R2, R3 I know, I put it back in the previous formula, so I can calculate the character function. So that is the basically the the idea of calculating the character function. Yeah, up to this part, any question?
Sir, what is the lambda part? Could you just re-explain once?
Okay. So what I'm saying that this weight, the elements of the weight tree, they form a basis, and in that basis, any representations I can write down. Okay, so this is a Dinkin level or Dinkin index for any representations. Okay, so that means basically if you know the representations, you know A1, A2, all those things, that you can write down as a lambda I, some vector, let me call psi I. Yeah, psi I is basically this thing. Okay, I runs from 1 to n. And once you have these relations, these lambdas, then you can invert this relation and you write down lambdas in terms of A. And once I know the element of this lambda 1, lambda 2 up to lambda n, so basically I get my lambda vector. Because lambda vector is basically an n-dimensional vector. I mean, it's n by 1 actually rather. So you get lambda 1, lambda 2, lambda 3 and so on. So once I calculate my lambdas i's, I plug it back and I get my R. That's all.
Okay, so separately we are calculating the rho and the lambda, and then we are just putting it into that equation to find the R, which is the final aim of the calculation.
Yes, yes.
Okay.
Okay. So let's see one example, and that I think that will be much more easy to visualize. Let's take the example of SU3 because SU2 is too trivial to miss out some important ingredient. So SU3, the rank is n-1, so 2. So as I said, that rank decide how many independent torus coordinates will be there. So there are the torus coordinates Z1 and Z2. And if you follow the previous rule, then you'll see that this is the relation between, so I have 3, epsilon 1, epsilon 2, epsilon 3, but they are function of 2 torus coordinates which are independent, Z1 and Z2. So you get these relations. Now, the denominator, which is called the van der Waals determinant, you start with SU3, so n-1, so epsilon square, epsilon 1, epsilon to the power 0, and you write down this thing. If you calculate the determinant, you basically get this function. And then once you get this quantity, then basically you can calculate the Haar measure. You plug it back here, and you get the complete Haar measure in this thing. So this is the total Haar measure you can compute for the SU. So now, how to calculate the R here? So for example, SU3 Cartan matrix will be 2, -1, -1, 2, because the Dinkin level is basically this blob, and they are connected by a single line. And this off-diagonal entries actually tells you how many lines are connecting these blobs, because each blob is represented by 2. Okay. So now in the fundamental lowest dimension fundamental represents the highest weight is basically 1, 0. So that you calculate the L2 by L1 minus alpha 1. So you get this quantity, and then L3 as L2 minus alpha 2, you basically 0 minus 1. So now you can see the lowest dimensional fundamental representation of SU3 is 3-dimensional. So as I told you, the multiplicity of the weight will give you the dimensionality. So that's what you can find out: 1, 0, -1, 1, and 0, -1. So that's why you have a 3-dimensional representation of SU3. So now this vector relation I have written down in terms of component here. So you start with some Dinkin level A1 and A2, okay, and then you write down as a R1, R2, R3 as a lambda vector plus rho vector. Rho vector is basically, as I told you, starting from n-1, n-2, and n-n here. So 2, 1, 0. And lambdas are basically, if you use the in previous relations, from there you can calculate lambda 1 as A1 plus A2, lambda 2 as A2, and lambda 3 equal to always 0. So you get the R. And once you know the A1, A2 for any given representation, you can calculate the R vector. And that's how you basically calculate the, the character function for that. So for example, let's say I took this three-dimensional representations, and three-dimensional representation, the Dinkin level is 1, 0, and if you plug it back, previously A1, A2, A1 is 1, A2 is 0, so your R vector is 3, 1, 0. So you plug it back here, you get the character function in this particular form in terms of epsilons, and the epsilons are related to this, so you write down this thing. Similarly, if I calculate the character function for the adjoint representation SU3, which is 8-dimensional, so Dinkin level is 1, 1. So if you calculate the similarly R, you will find out 4, 2, 0. You put it back in the definition of the character function, and if you calculate, you get this, definition of this characters, and this is the character function for adjoint representations. Now, there's a very nice way you can cross-check the property of the representation that you can check by the dimensionality. You should be able to check in terms of the character function. If you believe that there's a one-to-one correspondence between the representations dimension of the useful representation dimensions and the character function. So if you remember the Young diagrammatic technique, so if you calculate 3 cross 3 bar of SU3, what you'll get? 8 plus 1. So you generate 8-dimensional representations and a 1-dimensional representation, which is singlet, right? So then if I calculate the 3 bar character for the 3 bar and calculate the character for the 3, and then if I multiply, that should be the character, then 8-dimensional representations character plus the singlet character. Singlet character is nothing but the 1. And that's what if you can cross-check immediately that if my chi1 is basically 1, because it's a trivial one, and the anti-fundamental of the 3 bar representation is like this. So you can really cross-check that chi3 times chi3 bar is basically this quantity plus 1. So that's a nice way to convince yourself that whatever you know about the representations, you can play the same game with the character functions as well. Okay. Yeah. So any question up to this part? Okay. So now, this character function is fine, but now what about the derivatives? Because these derivatives are very non-trivial in a sense that you cannot treat them completely as a quantum fields, but also you cannot throw them out, because if you see, they behave like an on-shell object when you write down the operators. For example, you write down the kinetic operator for the scalar field, you write down d mu phi, d mu phi. Okay, it's actually there, right? So that means we need to give the status of this derivative as a quantum field without treating them as a completely as a quantum field. So these derivatives are basically do not transform under the internal symmetry groups, but they do transform under the space-time symmetries. Okay, and because of that, depending on the derivative, we have two more important aspects in the quantum field theory, which are basically equation of motions and integration by parts. Okay, and which we are discussing last time. Also, I'll be discussing more when I talk about the more explicit operator structure. But the trouble is not there. The trouble is when we talk about the derivative of the space-time symmetry, the space-time symmetry is not compact. And the computation of the character function that I calculated, okay, that is not applicable for non-compact group. So that's why, as I mentioned, a Hall measure is only defined for the connected compact group. So we cannot really do that thing. So what you have to do, first we have to equalize this SO3, 1, and we have to calculate this SO4, and we can express them in terms of SU12 plus SU2R. So instead of a direct representations, we'll go to some wild representations. And in this particular case, I'll consider all my lighter degree of freedom to be massless. So it is not a really bad idea to go to a wild representations, and I can construct everything in the wild representations, and then I can come back to the 4-component notation again. Okay. So now the trouble is when you do this equalizations, actually, that SO4 character when you write down in terms of SU2 and SU2R, they are not exactly same. So what I'm trying to tell you here, that if you think about the character functions of these non-compact representations, you can write down in terms of some compact groups, in this case SU12 plus SU2R, but this is not true that if you know the SU2 character, and as you have learned from the last few slides, we cannot just multiply them and get the SU4 character here. If you are coming from a non-compact representation, there's something more than that. So that's what I will explicitly tell you how you write down this character function. For example, in the SO4, when you write down, there is the spins you write down in terms of L1 and L2. And when you write down in terms of SU2L plus SU2R, there also you write down the spins, which are basically J1 and J2. So these are basically, in the parentheses, those are the spins we are talking about. So this is the representation of a scalar. So now what you are doing actually, so this, if you calculate the scalars, then you would expect they are not transforming at all. So in a intuitive way, if you go, then you will find out the character function is to be like this only. Okay, but this is not certainly true, because then we have to remove something called the d square, and this has an implication in the context of your equation of motion also. Okay, and we'll not discuss much detail, but I will tell you how to do that thing, in an outline way. And what about this guy sitting here? So this guy is related with something which is called the scaling dimensions. So that's why our symmetry group, when you talk about the space-time symmetry in this context, you are not restricted to SO4. Rather, you extend to a conformal group, which is SO4, 2. This additional 2 is the dilatation, which is basically for the free theory. This gives a scaling dimensions, and that matches with the mass dimension of the fields. So that's why this d to the power 1 stands for the scalar, d to the power 3/2 stands for the fermion, and d to the power 2 stands for the stress tensor, F mu. That's just the mass dimension. On top of that, there is another function which is called the momentum generating function, which is written in this particular format, where the alpha and beta are, the alpha is the torus coordinate for the SU2 left, and beta is the torus coordinate of SU2 right. So if you combine those information, so you can write down the character of those defined kind of spinors, okay, in terms of the SU2L times SU2R coordinates. So this, to achieve this, you need to really go through some detailed, tedious mathematical structures and computations, which is beyond the reach of this current lecture. But this is, for the time being, we'll take as a granted kind of thing. But what are the important messages there? It is not just the utilization of the Lorentz group. It's something beyond that, and that will help me to calculate the character functions in terms of SU2L plus SU2R character. And along with that, we introduce this momentum generating function. And the beauty of the momentum generating functions are that, along with this kind of character computation, they actually takes care of the integration by parts and the equation of motion. So now you can see this kind of mathematical structures, if we can develop, then once we plug in our statistics with these quantities, what will happen? That whatever the invariant quantities or the structures we will be calculating, we don't need to really worry about whether they're related to each other by the equation of motion or integration by parts, because those relations will be taken care of by this kind of mathematical functions. And that's why for any given theory, you just plug in these quantities, okay? But whatever be your field content and so, you really don't need to worry and explicitly check them for case by case. And that is one of the most beautiful and attractive part of this whole construction, that you don't need to really check the equation of motion or integration by parts case by case. You can really calculate the independent number of invariant quantities. Yeah. Any question after this part? Okay. So let me give you some more, inside view about this IBP. So now, what is this IBP is doing? So if you think that what kind of operators you would expect to be related to each other by the IBP. So if you have a prior knowledge about them, then you can really, think about, okay, so if these two operators may be related to IBP or not. If you see carefully, the IBP is not introducing any kind of new fields. what it is doing actually, it is actually changing the position of the derivative operator. Okay, so that's why any operators which actually have the similar constituents in terms of fields and derivatives, they may be related to each other by the IBP. So here's a nice example that if you take a total derivative of this structure and you say that, okay, I don't have any boundary, so all the operators are basically setting to be 0. This doesn't leave any kind of impact in your analysis. So you'll get del 4 phi r minus 1, and then another term you'll get del cube phi del phi r minus 2. If you see, the number of phi field in both the structures are basically same. R number of fields are there, and you have 4 derivative operators. But the position of the derivative operators are different from this to this. And that's why either in your analysis, you will include this operator or this operator, not both of them. But this tells you that if you change, and you can have multiple times of IBP and you get different kind of structures. For example, you start with a phi 2 del 4, you can write down del 4 phi, and then del cube phi and those things. So in this way, you can find out all possible, the structures which can shuffle the position of the del, you can construct. And what you do actually, you collect all of them. And when you collect all of them, that's what you basically calculate in this through this mathematical principle. And this collectively what you get is nothing but my momentum generating functions. And that's the reason actually momentum generating function, when you introduce in your theory, that takes care about the IBP. Okay, so this goes to many intermediate steps, but I'm trying to give you, hand-waving way that why these things works, and one can come up with a mathematical principle to take care about this quantity. Okay, yeah. Any question about the IBP related things? Okay, so now coming back to the definition of the platistic exponential, that what we have started with. Yes.
Hello.
Yes.
Yeah. Can you go back to the previous slide?
Yes. This one.
Okay. Yeah. So just a second. Yeah. Yeah. So the thing is that the IBP and total derivative that you mentioned last time.
Yes. Yes.
It's I'm still thinking that they're basically same thing, right?
They're basically connected to each other. Yes. Yes,
Okay.
they're basically connected to each other. But in some cases, if you introduce the boundary, okay, then you cannot set them to be 0, but still I get a relation. So IBP relation I will still have, even the total derivative term is not 0.
And then you say that the momentum generators.
Yes.
I actually, yeah.
Yeah. So if I calculate this quantity, okay, so let me tell you why this minus 1 to the power k, because every time you get IB integration by parts, it becomes minus sign. So that's why this minus sign, minus 1 to the power k is there, permutations. Okay. And if you add all possible structures for a given representations, and if you add them, there's a way to add them, then you get this function. So that's why. So this momentum generating, and this is called in a conformal symmetry language the momentum generating function. Okay, and this momentum generating function actually come up is giving the exactly same result if you do in this way. That's why the IBP and momentum generating function are related to each other, and that's why it guarantees that if you introduce the momentum generating function with the statistics, I'll show how, and then you are taking care of this constant due to IBP. You don't need to explicitly check.
Okay. Okay.
Okay.
Thank you.
Okay. Yeah. Okay. So yeah, any other question? Okay. So now, so what we have now? So initially, the first part of today's lecture so far, we have learned how to calculate the character function for the connected compact group, and that because we are dealing with the internal symmetry, the connected compact group, right? So then we know how to write down the character function for the internal symmetries. Fine, we keep aside. So then we talk about the space-time symmetry, and without going into too much detail, and mostly the hand-waving way, but addressing what are the key features of that thing, we can calculate the momentum generating function and the character non-compact characters in terms of compact group characters, right? And then we can now introduce the impact of the space-time information. So now when you introduce the space-time information, automatically now I am in a platform to compare the spins of different particles. So now that's why the total statistics is basically contains for the spinors, I'll write down separately. For the scalars, I'll write down separately. And for the field strength tensor, I'll write down separately. So spin half, spin 0, and spin 1. That's what I'm restricting, because this is the toy example of the standard model effective field. You can write down. So now total integration measure also write down for individual things. So this is for the SU3, SU2, U1, right? And I am not imposing further baryon number and electron number symmetry. So that's why their measures are not included here. These are the internal gauge symmetries. And these two are basically my space-time symmetry, SU2L and SU2R. And this 1 by P4, this is basically to take care about the integration by parts. So my new definition of the Hilbert series would be total measure times the total statistics. And that's all. Now, if I perform all this integration, but remember, though it looks very complicated, but each integral is nothing but finding the residue of each coordinate systems. So there's if there are n number of coordinates, cross coordinates there's n number of kind of residue theorem you have to perform, and you get basically those results. Okay, and here importantly, in which order you perform the integral, that will not matter. So in that way, this is very simplified. So in this way, you can calculate the full hard measure and the Hilbert series. So now, if you want to learn this thing in more detail, so as I told you, this actually includes very detailed mathematical structure, and it requires more time to discuss. So I have given you the link here where I have given this 5.5-hour lectures on just this part, how to calculate these effective operators. Now you can understand why it is not possible to discuss everything. But if you are interested, you can follow this link and you will get the whole 5.5-hour lecture just dedicated to this part. Okay. So now, once we have this mathematical principle, now what we do for our colleagues, we have introduced and we have written a mathematical program which is called the GRIP. It's a short form of the group invariant polynomial. It's a mathematical based package where we can give the information about the different kind of symmetries and the field content, and you'll get different kind of .m file. There are some example files are there, okay, and you can calculate the character function especially for different representations, and different models actually you can calculate. So far what we have done actually, we have been very futuristic, and we are assuming that in near future, in the experiment, we will find out some new particles, for example, either real singlet scalar or singly or doubly charged scalar, or different kind of fermions, or some kind of dark matter candidate, and so on. So in all these cases, we have considered standard model is extended by these particles, then how to construct the effective operator. So these, considering as an infinite degree of freedom, the SMAP will not be sufficient, right? Because if you discover something, if you observe something on shell, that means that you also include them as an infinite degree of freedom. So then you have to extend the idea of the SMAP, and something you have to calculate the beyond standard model effective field theory, which is called BSMAP, and all the different kind of phenomenological interesting examples we have computed. So if you are interested in some of them, you can just have a look into them. Now let me tell you how this works actually. So you start, there's the basic simple, there is just a directory, and you just get the model, for example, a standard model, okay, and then basically you call the main program, and then automatically you will find out the input table here. And this input table displaying, you can cross-check the input quantum numbers that you have given, they are actually correct or wrong, right? So this actually you can immediately at this point, you can cross-check before proceeding further. Now there's a very nice comment called the display Hilbert series output. So what are the flexibility you can do? You can say, okay, so I'm restricting myself to dimension 4 to renormalizable Lagrangian. So you write down 4. If you want to calculate up to dimension 6, you write down 6 here. And then it will give you all the operators up to dimension 6. And then if you say only mass dimension output, that means basically if you say 6, it will give you the operators only dimension 6. If you put it false, then it will give you all the operators up to dimension 6. Here you can mention, for example, baryon number, electron number conservation. So that's set to be 0. You can change the flavor. We just put 1. But you know, there are some operators which exist only when you have a more than one number of flavor. So that you can check NF, then you'll see the number of operators are function of NF. So that you'll get also here. You can change the number of flavors. If you want to calculate some specific baryon and electron number violating operators, and then you can say which amount of baryon number electron number violation you want to do, you put that quantity, okay, and then you can say some upper limit, some there's a 10 or 12 or 15, and then you expect to get that operator within that, and then you'll get the operator. Okay, so in this way, also you can save those output in a particular file, and so on. You can play around with this thing. And this is the input file you have to, that is already there. You can just edit that thing. Let me tell you how you can do that thing. So for example, when you define the Higgs scalar, you define, there's a field classes are defined. So there's a Higgs, you define like, you can give a name. Okay, you should not give a name in a LaTeX format. You just give a name in a simplified way, text format. And if it's not self-conjugate, if it's not real field, then you can say it's a false. And then you define scalar or Fermion, which will pick out its Lorentz behavior. If it's a scalar, it doesn't have a chirality. Because we are working in a while basis, so it has a chirality either left or right. So depending on that, for the Fermion case, you can define the chirality left and right, and you give all the quantum numbers, and that's all. So in this way, you can define all the scalar, Fermion, and spin one fields are defined as a tensor field. And you know, in this way, you can define the representations. So now one of the interesting aspects is there are many ways one can make mistakes. So we ask them not to do so. For example, if you're giving the information in terms of dimension of the representations, either you give dimension or you give Dynkin level in this way. So when you representation should be given like this, and dimension, a Dynkin level should be given like this, but you should not have a mixed way. Either you give this format or this format. So that's why these are forbidden format. Okay, you should not do that thing. If you have two different represent same group but multiple times, for example, left symmetric model, if you have SU2L and SU2R gauge group there, so you should not write down only SU2 because you need a discriminatory for that. So that's why you have SU2L and SU2R. Okay, and so that's how you can define this input file. Also, when you define kind of tensor field for the left and right chirality, because you're working at while basis, so then you should not use as a suffix or prefix, you just put as a text format. See, if you avoid this basic and maintain this basic thing, you should not face any kind of problem to calculate. Fine. So now, when you calculate this dimension 6, so how do you can display those output here? As I told you, so basically the output that you will be getting is basically nothing but in terms of the polynomial. So you can see that these are not the covariant form. These are the polynomial form. And see, I have given the number of flavors as NF. So each operator having Fermion fields, the number of operators depend on the number of flavors also. So that's why the NF dependency come into the picture here. Okay. And if your NF is integer, the whole quantity is basically, there's no fraction. The total number of operators is basically an integer. Okay. And one of the, for example, baryon electron violating operator, for example, if you want delta B to be 1, delta L to be -1, and you set up to dimension 15, then automatically you see the first time when you have an operator which poses this baryon and electron violation by 1 and -1, it will, spit out that operator. For example, here at the dimension 6 level, you get this operator. So you don't need to really check beyond dimension 6. But it may happen if you change them, the operator appearing that for the first in dimension 8. So you'll get that operator dimension 8 level. So in this way, you can calculate different kind of invariant polynomial structures and the the baryon and electron violating operators, but still in a polynomial form. Yeah. So before proceeding further, if you have any question. Okay, so now the question basically, we have this polynomial, right? So now we should be able to write down the covariant forms of operator using our field theory knowledge. And here you can see that D is nothing but my covariant derivative. And as I'm saying, these are just the spurion, so it doesn't matter the ordering and all those things. So one, using the quantum field theory knowledge, one has to organize them in a covariant form. So what are the covariant form relation and the polynomial? Let me give you some example. For example, if I give the polynomial in a 5, 6, and if I have a H, which is a complex doublet, then automatically I know that H dagger and H, that should appear in the same number. Otherwise, this will not be invariant. Okay, so that's why it's the H dagger H whole cube. If my polynomial is written as a 5, 4, D2, so then I'll get this 2, which is very important. So let me tell you why this is important. Let me show you the 5, 4, D2, if I can find out here. Let me see. 4, D2, okay. Not necessarily. Okay, so I'm unable to track here the 5, 4, D2, for example. Let's take, okay, yeah, so this one. Now you can see the polynomial gives you 2H square D2 H dagger square, right? That means that with 2H dagger and 2 covariant dative, you should be able to write down 2 independent operators. And this program gives you 2. That is the important aspect of this thing, that using equation of motion constant and the IBP, you should be able to write down how many independent operators. That's why you don't need to really do by hand and check them. So this 2 is important, and that's what is written here. That's this 5, 4, D2 class, we have 4 scalar field and 2 covariant dative. We should be able to write down 2 such operators. And if you see in the dimension 6 chart, we'll see soon, then exactly we have 2 different operators, independent operators you can write down, and whatever the other structures we'll be writing, including these 4 scalar fields and 2 covariant dative, they'll be related to either these 2 by equation of motion or IBP. Similarly, for X cube class, which is the field tensor cube class, we'll have these operators, okay, and then psi square 5 cube, we have these Yukawa kind of structures, and so on. So you have this kind of polynomials, and these actually you can translate in terms of the, in a covariant form, the operators. So now the question basically, there are some thumb rule we have mentioned in our paper. While constructing, we should be careful about few things. For example, if you have a polynomial inside dagger psi, phi dagger phi d, where to put this d? Between here, these 2 phi or psi. I can have in principle write down this operator from here, or I should be able to write down either this operator from here. Okay, but interestingly, if I write down this operator, then you see you can use the equation of motion of the fermions. Okay, and then you can rewrite this operator in terms of psi square phi cube class. But you have seen already in a previous class that along with that, we have this operator also. That means we are generating this operator independently. So if I write down this polynomial in this particular form, then effectively I'm writing again this operator. That's a mistake actually. So then this is the only choice we have to do. So with this polynomial, this will be translated in a covariant form in this particular. But if I do not write down this operator, but if I'm writing, then I should be able to write down this operator. So that's how there are a lot of thumb rules we have set. For example, d mu x mu whole square, right? So then if you use the equation of motion of the field tensor, okay, and then you can write down, it's a combination of 3 such structures, psi bar psi whole square, which is like a 4 fermion operator, okay, 4 fermion dimension 6 operator. We have a phi square, phi 4 d2 operator is there, right? And then we have a phi square d and then psi square, this operator. So
Jaideep,
yes.
so when you're talking about that, you're using equation of motion. So what kind of equation of motion you're saying? Is
Okay,
it
so,
free theory of equation of motion?
Yes, yeah. No. So basically, when I'm talking about the dimension 6, I'll be taking the equation of motion of the full theory up to dimension 5.
Okay.
All the interactions and everything.
Okay. And also, if we use equation of motion, then when it may not be on-shell, right? It can be off-shell thing. So why we are using equation of motion?
No, all these are basically on-shell objects, right? So that's why I'm taking the on-shell equation of motion.
Now, at the Lagrangian level, why they should be on-shell?
No, because these are not the infinite degrees of freedom. So in this construction, all my IR degrees of freedom are treated as an on-shell object. Because these are my asymptotic states. Because this construction is giving a point local interaction, right? the point-like interaction. So inside the loop and all those things, you do not know. It's a black box. It's basically give you the external states only. So all my external states are basically on-shell objects.
Okay.
If it's not on-shell, then it cannot be appear as asymptotic states.
And if I just to confirm, if
Yeah.
you are writing operator up to certain motion should be taken up to dimension 5, right? Operator.
Sorry, Sanjay, I could not hear your last 2 lines.
Yeah, I'm just saying, let's say we are interested to, let's say, write down all the effective operators up to dimension 6. Then the equation of motion, as you said, I'm just confirming, will
Dimension
be
5.
of a given field will be taken up to
Dimension
whatever
5.
it is satisfying up to dimension 5, right?
Yes. And if, for example, there are a lot of literatures recently, when you calculate dimension 8, then you have to calculate the equation of motion up to dimension 6 or 7.
For certain kind of or any dimension 8
For
operator.
example, when you integrate out, okay, then lots of redundancy will be there. To remove the redundancy, you have to use the equation of motion. So
Yes.
if you, in the dimension 6 level, there will be redundancy. Now, if you use the dimension 4 equation of motion, that will remove the redundancy and you will get only dimension 6. But that's the incomplete result. You have to plug in the dimension 6 equation of motion in the dimension 6 redundant part, which will give you dimension 8 operators.
Okay.
So that's why the idea is, if you are working up to d dimension, you use the equation of motion up to d minus 1 dimension.
Okay.
Okay. Hello.
Thank you.
Okay. Yeah. Is there any other question? Okay. So now what I was telling, that now you can see that if you have now this operator, phi dagger phi, phi dagger box phi, okay, this is related to now actually this operator, either this operator or this particular operator through the equation of motion, right? So that's why these are 1 or 2 examples. But what we have done actually in our paper, we have listed all possible scenarios that one can possibly encounter and making make a mistake while translating from polynomial to covariant form. So one has to be just be a little bit of careful, and one should be able to write down all the covariant operators. And that's the best thing to do. Write down and the dimension 6 to dimension 6 covariant form, polynomial to covariant form, because the results are there and you can cross check with that thing. Because then what you can do, you can extend your number of particle content if you want, for example, by a right-hand neutrino or a singlet scalar, and then that will give you more operators, and that's the more involvement is there. So equation of motion, all those things, right? So that's you can calibrate that knowledge and you write for the new effective field theory for that thing as well. Well, so now in the Fermion sectors are much more tricky in a sense, because Fermion sector have this different kind of fermions are there. One is the lepton, one is the quarks. Now some of the quarks are basically SU2 doublet, but all of them are SU3 triplet, right? But some of them are SU2 singlet also. But in the lepton sector, all are SU3 singlet, but they are basically SU2 doublet. So that's why the Pauli spin matrices and the Gell-Mann matrices also play a very crucial role here. For example, if you check the polynomial that we have written down for the dimension 6, there will be one term associated with L bar L whole square. That means with 4 lepton, you can write down only one operator. But in principle, you should be able to write down either this or this. But if you see that if these fields are exactly same, then you can use the Fier's identity, okay? And then you can write down exactly this to this. That means these two are not independent. And that's what actually this Greek actually takes care about that part also. So either you write down this part, you will not be misled by that. But if you now change the same dimension operator, but 2 lepton field are replaced by 2 quark field, then you will see their phasing is not very trivial, because their flavor indices are not exactly connected to each other. So there, because you are expecting them to be baryon and electron number conserving, so your flavors are also very constrained from that aspect. So that's why you will get 2 different structure, and phase will not allow you to go from this to that. So that's why in this case you'll get only one operator, but in this case you'll get two operators. Okay, so these are the small but important things one has to be very careful while writing these operators. And once you include more and more fields, things become slightly more difficult but doable. And yes, so now you can see that these are the basically I was talking about the dimension 6 operators. So now you can see the phi 4 d2 operator. You can see you can write down only these two operators, right? The phi dagger phi 8 and then box phi dagger phi box is the DL number operator d2 d nu or this operator. But there are different literatures and different bases you can choose, and where they may not be looking this thing. But what is important that whatever the choice of basis is, that you should not be able to write down more than two independent structures. The independent structures could be looking different, but certainly not more than two. And that is true for other thing as well. And that's how you generate all the dimension 6. Okay, if you do not consider the flavors and all the Benin number electron violations, then you get 59 total dimension 6 operators, and yeah, which are basically independent and not related to each other by the equation of motion and integration by parts and so on. So that's how you actually cross-check the result, and you can extend this result beyond dimension 6 and depending on your necessity and requirement. Yeah. Okay. So up to this part, any question? Okay, so this was all about the construction. So now let's try to understand the bottom approach in a specific, more from the field theory point of view. So now let's consider the standard model effective field theory. So when you consider the standard model effective field theory, it automatically implies that your sorry. So that automatically implies that your low energy theory is basically your standard model. Now you're looking to some kind of scattering, let's say standard model particles, they exchange a standard model particle, and there's another standard model pair of standard model particles up there. Now, when you include the higher dimension operators, how do you add them? You basically have a renormalizable standard model Lagrangian, and then you add these effective operators. Now you see, because they are starting from dimension 5, that's the lambda to the power j minus 4, j runs from 5. So the dimension 5 operators are subtracted by 1 by lambda, dimension 6 are 1 by lambda square, and so on. And why this I? Because in every dimension, you can have multiple operators, as we have seen in a previous 2 slides. The dimension 6 level, we have this 59 baryon and electron number conserving flavor blind operators. So then for each dimension, you have a different operators, and for each operator associated with some kind of coefficients, and these coefficients, we just assign them by hand. We do not have clue what are the origin of this. That's why they are the free parameters. So these C are the Wilson, as a specific name, they are called the Wilson coefficients. So there's each Wilson coefficient associated with each operator are independent, and so the uniform cutoff scale that I'm using here, the lambda. And this Wilson coefficient, as I told, there are 3 parameters. So now when you add these, now the same scattering process have some additional contributions. How? Now you have this diagram, and now this is a blob kind of diagram. And what is this blob? This is a local composite operators that is generated from this thing. For example, if you have 4 Fermi theory, then you know there is a psi bar gamma mu psi, psi bar gamma mu psi. That effective operator is there. So then automatically that point interactions you have to add. Now the total amplitude of this process for the standard model effective field theory will be this plus this. Okay, and that's how your and these blob interactions, which is actually to this Wilson coefficient and the lambda, the BSM effect should be there, right? Because all the BSMs are basically hidden in this particular context, and this is the effective operators. And how are these operators? And that's what we learned today, how to construct these operators. Once we know this operator, we can add this operator with our renormalizable Lagrangian, and now we can recompute those scattering processes that we have computed only using the renormalizable part, and we can see there's a certain deviation in the which are proportional to this C. Okay, and that's where the experimental data will play a crucial role. Okay, and that's how we talk about later more in a rigorous way how to fit that thing. But this is a just to give you an idea how in the bottom-up approach, when you add these effective operators and you make your Lagrangian extended by the renormalizable part and the effective part, how the additional contributions can come into your picture. Okay. Yeah. Any question after this part? Okay. Fine. So now we'll move to the another complementary approach, which is called the top-down approach. So now the top-down approach, the main notion is basically learning the integration out. So you start with the UV theory, unlike the previous case. Here I know what is my UV theory. Okay. So, and then I can understand looking to the Lagrangian, okay, what are my UV interactions? What are my UV fields? Okay. And then I'll set the mass of those UV fields with such a heavy compared to the standard model particles that if I integrate out, then I should be able to write down a cascade of higher dimension operators, and each operator should be suppressed by a scale, right? And then we'll see that those scales and the Wilson coefficients are not completely unknown to us, unlike the previous one. So how these things work is as following. So you start with the high energy theory, okay? You integrate out those heavy modes, okay? And that's why it's called the top down, because you start from the heavy scale and down to the low energy scale, and you construct the low energy effective field theory, okay? And that actually in the principle you set some kind of suitable limits in this process. And the main important part is basically to calculate and to perform the integration out. There's a different method to integrate out. And another important aspect is basically when you integrate out, then at this energy scale, there will be some kind of matching, because you have a UV theory, you have a low energy theory, effective field theory, and at that scale, you have to perform the matching. So how to perform the matching? That we'll learn. So before going to the field theory, let's talk about a very simplest case. Let's consider the scattering in a one dimension case. So here we have, let's consider the square well potential, whose potential is given like this, and this is the width of the potential here. Okay, and then you calculate the reflection coefficients, okay, which you can write down in this way, and you assume this delta to be very small quantity, and this momentum transfer, the K, is also very small, such that you can really perform this expansion in this delta square K square, and you can ignore this part. Okay. On the other hand, you have a delta function potential, which writing in this particular format, and eventually, if you look at this structure and this structure, as such, there is no reason that these two are related to each other. But what you can do, you can use this potential also, and you can calculate the reflection coefficient, and that will give you this formula. Now, if you see in case by case, what you can do actually, that you can say, if I set my G to be alpha sine alpha, then up to the order of delta square, this potential and this potential give you the same result. Okay, and that's what is called the matching. That means you have two different theories, okay, and with a interesting circumstance where the delta is very small, two different looking potential give you the same amount of reflection coefficient in an order by order. Now here you can check that this matching condition G equal to alpha sine alpha, is it a universal thing? No, it's not an universal thing. Why? Because I have ignored the higher order terms. So if I include the higher order terms in the expansion, then I will have a different kind of matching condition I have to find out. So that's what it's important to say. This is the matching condition, but up to this order, right? So this gives an idea that two different theories, okay, can be brought close together, and some energy scale or some length scale, they can behave in the same way. And that's the idea we are using when you integrate out. You have a UV theory, you have a low energy effective field theory, you remove, or in a formal language, you integrate out those non-IR modes, okay, and then you create an effective field theory and you demand that is very similar to the low energy effective field theory, and then order by order matching, you will get the relations between the parameters of the low energy theory and the UV theory. And that's how the matching gives you the relation between the UV theory and the low energy theory. And this way you can reduce the UV theory into a low energy effective field theory. So I hope this is the idea of matching and integrating out. The philosophy is clear, and then we will proceed in the context of quantum field theory. But if you have any question. Okay. So now, let's borrow the example of the effective four Fermi theory from the Standard Model. So we have this full theory for the Standard Model, right? The integral vector boson. So how to write down the two currents are there, and that is now the propagator is a sandwich between them. So this is the one current. You can write down here, and then another current, this one, and this is the propagator. And if you use this, supplying this gamma and all those things, so what eventually you write down, this is basically psi bar gamma mu psi and then psi bar gamma mu psi. And this is nothing but my four Fermi operator. Write down in the SMAP, we write down the psi bar gamma mu psi, psi bar gamma mu psi. And the coefficient we write down as C by lambda square. Now you see the lambda square is nothing but the MW square, right? So whatever we have learned, that cutoff scale or the this lambda, when the bottom up approach we introduce by hand, but now we know this is actually the mass related to the mass of the heavy particle that is being integrated out. So that's why in the top-down approach, when you integrate out, you'll get the operators and the mass of the heavy particle will actually use as a suppression scale. And that's why it guarantees the convergence of that partition series actually. Not only that, the Wilson coefficient here, if you see the Wilson coefficient in the bottom-up approach, when we throw in our theory, there's a free parameter. Of course, we don't have any origin of that thing. But here we know there's a gauge coupling in the UV theory we have, right? So that Wilson coefficient is a function of this gauge coupling. So at the low energy theory, which is nothing but a free parameter or an unknown free parameter. So this is related to some UV parameter here, which is of course a free parameter, but at least we know the origin of that. And that's how the matching condition here give you that GF is basically this point-like interactions related to G square by MW square. And we can use this matching condition for the tree level. Now, if you include the higher corrections, we'll see there will be corrections to these matching conditions. So we have to learn how to perform the tree level matching, the one loop matching, and so on. Okay. Yeah, so these are basically slightly different aspect of the normal quantum field theory. So I'm slowing down this part so that you should be able to appreciate this thing. And yeah, if you have any question, please stop me and ask. Okay, so there's no question. Let's proceed. Fine. So now let's relook to the top-down one. So we know what is the meaning of integrating out. We know what is the meaning of matching. But when you perform this integrating out and the matching, the effective Lagrangian that you are getting is not, it's not actually forming a basis, because still it has a relations among those structures. Why? Because we have to filter out the independent structures from there. So we have to again invoke the relations with the pairs, the integration by parts, and the equation of motion. And that actually is a tedious job, and you have to ask your program to do that thing. And this has nothing to do with the grip. You remember grip, that checking of the equation of motion integration by parts was from the bottom up approach. But this is a explicit checking of the fields of for your theory from a top-down approach. So one is doing a separate way. So that's the skeleton of this idea. We start with the UV theory. And for the BSM theory, when you write down the scattering, you consider the standard model particles as the asymptotic states. So you write down the process, which is basically standard model involved in new physics. Okay, you will have pure standard model process, and you have pure new physics process. Pure new physics, basically all the asymptotic states are also new physics. So we are not worried about them because they do not carry any information which will be important at the low energy. These will also be there in the low energy. This is the important part, because once we integrate this new physics, then this will reduce to a point interactions. So this process and this process together will give me this kind of structures. Now, if you recall the bottom-up approach, we start with this, we add these operators, and we get this thing. So now from the top down, we have these diagrams, and then we get back this thing. So now this similarly, we get the similar kind of structures of the effective operators accompanied by the Wilson coefficients and the cutoff scale. But these Wilson coefficients are basically a function of these couplings, and this cutoff scale are basically related to the mass involved in this new physics fields. So it's a basically similar description, but the interplay of the quantities are slightly different. The interpretations are slightly different. Yeah. So before I proceed for explicit, is showing you how to perform the integration out. If you have any gross question on this integration out and the top-down approach. Okay. So now let me tell you how you can perform the integration out. First, we'll see how to do that thing at tree level. Okay. And I'll not discuss in a loop level because it's not possible to discuss loop level here in this way, but I'll certainly give you the idea what are the source of those loop level contributions. Let's consider some UV Lagrangian, which is written in particular this format, and consider the capital phi is your heavy field and small phi as the light field. And you have the capital phi kinetic term, you have the small phi kinetic term, and this is the capital phi self interaction, for example, phi 4 kind of thing, small phi self interactions. And then you have the interaction term where you have a small phi light field and the heavy field both. And you can rewrite that quantity in this particular format where it can be linear in heavy field and all the other coefficient are basically functions of light field. Then you have phi square, you have a light field. And if you restrict yourself, the UV Lagrangian to be renormalizable part only, then at max you can have a phi cube because the phi 4 terms are basically dumped in the self interactions. So you have only this kind of structures. So then you can use the Euler-Lagrangian equation. What is the most important part? I am using the Euler-Lagrangian equation here. I am assuming that there is no derivatively coupled interactions here. So if I get time at the end of the other lectures, last lecture, I will talk about the certainty about them. But in most cases, they don't. But if you keep the derivatively coupled interactions, then you have to be careful about using the Euler-Lagrangian equations. You have to use the generic Euler-Lagrangian equations. But at this point, all my interactions are basically polynomial fields. So safely, I can use these Euler-Lagrangian equations. So then this gives me this definite Euler-Lagrangian equation, which I'm writing in this particular format. So then what I'm doing, I'm solving this equation, and this will give me nothing but my classical solutions, which I call a background field here. So background in a sense, because I'm removing the dynamics of these heavy fields. So I'll treat them as a background. That's why there's the classical solutions or the background field. In the leading order, contribution of the background field is written like this. So now, here we'll assume that the momentum transfer through this UV interaction that I'm talking about are basically small compared to the mass of the heavy field. That means the energy scale that you are talking about, looking at the UV theory, okay, is much, much smaller compared to the mass of the heavy fields that you are integrating out, such that we can perform the binomial expansion with respect to this. Now, why I am performing this is a normal, not normal derivative, but a covariant derivative. That's why this is called the covariant derivative expansions. And the reason behind is that the covariant derivatives, if you do a covariant derivative expansion, your construction is basically gauge invariant. And that's why we can perform this covariant derivative expansion, and we can truncate this depending on up to which order of the effective operators we want to generate. Now, let's say I truncate here, and then what I'll do, I use this phi c and then plugging back in my Lagrangian. Okay, and if I do that, then for example, the one of the first term, V5 phi c, will look like in this particular structure. Now, if you see that this is my effective Lagrangian, but this effective Lagrangian is described or written in terms of light fields only. So I have removed my heavy fields through this expansion or using these classical solutions. This method is called the coherent derivative expansions. Okay. Now, when I do that thing, then I can recast my whole VSM Lagrangian now in terms of standard model Lagrangian, and I'll rewrite them depending on their dimensions, dimension 5, dimension 6, and so on. And these lambdas are nothing but the mass of the heavy field, which I'm integrating now. So these C's here are called the Wilson coefficients, and these OJ are the effective operators. Okay. And this lambda is basically nothing but my cutoff scale, and this cutoff scale related to the mass of the heavy field. And why I'm saying related? Because you can have a multiple heavy fields. The regular choice of the cutoff scale is generally the lightest among the heavy fields is the choice of your cutoff scale. Okay. So let's take, but yeah, before going to one explicit example, if you have any question.
Maybe you can have some questions because it's we have 5 minutes. So if there is any questions, we can take some question. Otherwise, you can just complete this example also.
If I think if I say the example that they can immediately connect.
Yes, yes.
That's the T-level part only. And then after that, we can take more questions.
Sure.
But if anyone has a small brief questions at this point, they can ask it. Okay. So now let me give you one explicit example that I think will be more clear. Let's consider you have extended your standard model by additional Higgs doublet, 2 Higgs doublet. Okay. And that is basically giving it a color singlet, right? It's isospin doublet, SU doublet. There's a hypercharge minus half. And that is written in this particular format. You know that if Higgs is a doublet, the I sigma to Higgs H star is also an SU2 doublet. The 2 bar. And then you write down the VSM line. Now you can see that while integrating out, I need to focus on the only heavy field involved Lagrangian. So I don't need to really at this point worried about what is my standard model Lagrangian. Okay, so I keep that thing as a low energy Lagrangian. Now I have written down this Lagrangian where I am focusing on where the heavy Higgses are there. So see, these are the parts where basically this is the trilinear couplings. Eta H is there, and I am not imposing any kind of discrete Z2 symmetry. Otherwise, this kind of terms I can write down. So I'm saying, okay, there is no discrete symmetry. So I have this trilinear interaction. And these are the quartic interactions, the quadratic in individual fields. Now, if I solve the Euler-Lagrangian equations and I expand over the heavy field Lagrangian, then the heavy field, so maybe the heavy field is capital phi. So, the capital phi. And then this capital phi, the classical solutions, you can write them in this way. Now see, it's very interesting to note that this whole thing actually depends, other different terms and fields are there, but it is actually proportional. Each terms are proportional to B. Even if you expand the all other higher terms, you'll find it is proportional to B. What does it mean? It means basically B is the trilinear coupling, right? Which is basically eta H. So if you switch off this term, then your phi C at the leading order will be 0. That means at the tree level, you cannot generate any operator. So now, looking into any Lagrangian, even before performing any integration out, you can immediately check if there is any kind of trilinear kind of interactions in heavy field. Then only you can generate a tree level operator. Okay. If you cannot, then automatically the leading the operators generated at the leading order would be at the 1 loop. So that's what you will see, that if I plug in back phi C here, then what I'll find out, I generate a eta H, H dagger square is already there, H tilde dagger is already there. The phi is basically replaced by this quantity, and which is basically eta H in this particular form. And from there, you generate a dimension 6 operator. Because the standard model Higgs is the higher degree of freedom, so you generate dimension 6 operator here. And look at the Wilson coefficient. The M is the mass of the heavy field, that is the lambda square, and eta H is the Wilson coefficient, right? And as I was telling, if there is a trilinear coupling, this should be 0. There should not be any emergence of this, and that's what you expect. It should, the strength of the operator should proportional to eta H. In the limit eta H tends to 0, this operator vanishes. It will not be emerged at the tree level. This can emerge in the loop level. Okay, so this is one of the simplest tree level example where you can generate the effective operator through some simplified scenario. I think is the best time to stop today, and then we'll continue from this tomorrow.
Thank you, Joydeep. Questions and comments?
Sir,
Yes.
yeah, so sometimes written in the literature that they have taken this lambda to the 1 TeV or 10 TeV something. But when you are constructing your SMEFT, there is nothing, no particle, no heavy particle is there with that much amount of masses. So like why they are taking this? You said this lambda would be the smallest mass, like
No. You heard me wrong. If you have a multiple heavy particles, okay, then lambda is the lightest heavy particle, not the light particle. Lightest heavy particle. So for example, let's say,
like,
for example, if you have a two heavy particle, 1 TeV and 5 TeV, the lambda will be 1 TeV. That is the general choice.
okay, like then also like in the SMEFT, like you gave the wave of the all the particle, they get the like their mass getting some correction and all those things. Then only you don't get any particle with like 10 TeV or something like mass.
No. There are two things. When you consider the SMEFT, which is a bottom-up approach, in the bottom-up approach, there is no heavy particle. You do not have any clue about the particle. You just add the effective operators by hand. So you choose the lambda to be by hand. 1 TeV, 10 TeV, 5 TeV. And actually you do not choose. You actually fit with the data, and that will tell you what is the minimal choice of the lambda. That's a different thing. Here I'm saying you have a UV Lagrangian, you have a heavy particle, and then you are integrating out the operators that you will generate. Each operators will be suppressed by the mass of the heavy particle. Now, this is a parameter. You perform the fitting or perform the analysis with respect to the data, and that will tell you what is the value of eta h square by m square that is consistent with the data. It's not us to set this. It is the data who will tell the value of this allowed value of the eta h and m. Right? So m equal to 1 TeV is a naive, intuitive choice, but it's not any robust thing to do. Data should tell this.
Okay.
Yeah.
Any other questions or comments?
Sir,
Yes,
sir,
your voice is not coming somehow. Or mouthpiece from Sanjay, then. Hello.
Hello, sir.
Yes.
At starting, the mass dimension of the heavy field phi is what? In the Lagrangian LBSM.
Yeah. Why? Okay, so I have chosen this to be scalar field. So you know the mass dimension of scalar field is 1.
1. So after putting the phi c, some dimension 6 terms are coming. That is.
But that dimensions are basically in terms of the lighter degree of freedom. There is no heavy field anymore.
Lighter degrees of freedom, but this sir,
Sorry, your voice.
H has mass dimension.
H, yes, of course. It's a standard model Higgs. So it has a mass dimension 1. So all the scalar fields have mass dimension 1 because I am working in a 3 + 1 dimension.
But this phi c has mass dimension. Phi c has mass dimension 3.
Phi c has
There
mass
is one
dimension. No, phi c has a mass dimension 1.
Oh, there is a m squared is there in the okay.
Yes.
I had not one.
because it's scalar field background, so it has a mass dimension 1.
Sir, one small question.
Mhm.
Sir, is this always guaranteed? Like if I have a theory in the in the new physics scale, like lambda scale, and I like the run down my theory to the low energy effective field theory in the MAB scale or something.
Mhm.
So during this running or matching calculation, it is always happen that my UV divergence will goes out.
No, the idea is basically the following. So you have a UV theory, right? So now UV theory may have both divergences, UV divergences and IR divergences, okay? Infrared divergences. So now you are constructing a Lagrangian, effective Lagrangian. So effective Lagrangian, that is a higher mass dimension operator, but your UV Lagrangian have only operators up to dimension 4. So if you trust the power of the renormalizations, that tells you only those operators you can renormalize, okay, which are basically present in the Lagrangian. So that means effective operators were not there initially. So of course you don't need to renormalize them. They will be always finite. There is no divergence associated with that thing. But they may have some kind of IR divergences. But when you perform matching, the matching tells you the IR divergences at the low energy effective field is still there. So in the matching, the IR divergence will drop out. So you don't need to really worry about the IR divergences. Okay. So that's why in the perform matching for the effective operators generation, you don't need to worry about the UV divergences. UV divergence will appear in the process of integrating out, but that will affect your operators which are less than mass dimension less than equal to 4. And that's why when you renormalize your theory, you perform the integration out, and then you have to renormalize your theory again.
Via this process, they will this divergence will goes out. Like for a process, particular process, I am saying like particular process in the it's SMAP, and I'm like integrated down with my heavy fields and like run down my theory to the low energy effective field theory. So this is always guaranteed. Like my IR divergence will be still persist, but my like UV divergence will goes out.
For the effective okay, so okay, that's a different thing. So now you start with a Lagrangian where you have added the effective operators. Okay.
Yes, yes.
So because you're starting with the effective operators, now if you calculate the loop in the quantum corrections, of course there will be divergences for the effective operators as well. But these are important because these are nothing but my anomalous dimension matrix. And that from there I will calculate the anomalous dimension matrix from those UV divergences, and then that will help me to run down the effective operators. Okay. So that's how you calculate the anomalous dimension matrix. Hello?
Yes, sir, got it.
No.
Any other questions? If it's not, let's thank Jyoti for today's lecture. We'll meet again at 3 tomorrow. Okay, thank you, Jyoti.
Okay. Okay, so
You can send me the link again.
yes, I'll send this thing. Yes. Okay, let me stop my recording then.